So I'm Trott. I'm from Sandia National Laboratories. I'm also one of board members of HBSF, and I've been spending practically my entire career at Sandia, my entire time in the US, working on COCOs. And today I want to give you a talk on unified memory. And unified memory is something which has been floating around for a long time. And I've been struggling with that for a long time. A lot of the codes I support have been struggling with it. And I thought it might be useful to give, the, unvarnished truth or something like that on this whole topic. And so that's my talk, right? Is unified memory an actual, long-term strategy, or maybe just supporting Crutch? Who here has heard stuff like that from vendors, right? Unified memory, it's going to be great, right? Don't worry about, memory migration. Don't worry about, where your memory lives. Just use it, and everything will work perfectly fine, right? The first time we heard that for real was probably around, 2015, 16 or so, in preparation for the first NVLink-based systems from NVIDIA. These were like the machines Summit and Sierra. They came with NVLink between the power chips and the NVIDIA GPUs. And the idea was that that would make all our lives much, much easier, right? It wasn't just make the connection faster, right? It makes our life easier, right? It would simplify our data handling, right? All memory is always accessible from everywhere. It eliminates the need for you to think explicitly about memory movement, when to migrate from CPU memory to GPU memory. It would allow you to oversubscribe your GPU memory, right? Yes, you only got 16 gigabytes on a V100, but you can have a terabyte of memory on the power chip, and it's perfectly fine to just allocate a terabyte of memory and then go through that on the GPU, right? And it would make sparse data access easier and faster, right? You have like your big database in the DDR memory, and then you just like randomly access it from the GPU, right? That was kind of a pitch of what this would achieve for us. Now, one thing I want to make clear is, right, like this is a confusion which has, been flying around for a while. There's actually two things, right? There's unified address space and there's unified memory. Unified address space just means that you have unique addresses, right? That you don't have like an address 0001 on the GPU and an address 0001 on the CPU, but we actually point to two different memory allocations, right? So unified address space just means that your addresses are unique, right? If you have a GPU address, that address will never be used by any CPU memory and vice versa, right? What that allows you to do is, in principle, and there's APIs for that, for example, in CUDA, you can actually from an address, or you can query an address and figure out, where does this memory potentially live, right? You could distinguish between CPU addresses and GPU addresses. That was actually, in the beginning, really easy, right? The address space of the GPU was super high shifted compared to where all the memory of the CPU was. And so, back in the day when I was debugging on the initial kind of Kepler systems, I looked at the address and I could tell you not only this was GPU or CPU memory, I could even tell you, this is GPU 0 and this is GPU 1, right? Unified memory space is different, right? Unified memory space means it's accessible from everywhere, right? Having unified address space doesn't mean that you can dereference the pointer from everywhere. It just means that the addresses are unique. Unified memory space says you can actually dereference the memory from everywhere, right? You allocate somewhere, and then whatever mechanism is underneath will move that memory so that you can access it, right? Or use some mechanism to access it, which makes it work. All of our current HPC platforms feature some version of both, right? All of them have unified address spaces, and all of them have some version of unified memory space as well. The only systems I'm aware of where neither of these exists are some types of embedded systems where essentially that unified address space doesn't even exist, where addresses could be overlapping. Now, unified memory has been overloaded quite a bit for a long time. And at this point, there's like 4 kind of major versions of unified memory. The first one, that was the earliest one, was essentially a mechanism which migrated allocations. So in the initial kind of like, NVIDIA's unified memory approach, we called it at that point UVM, Unified Virtual Memory. What we did is we actually duplicated allocations. Right, so your allocation existed on the host and on the GPU, and depending on where you access it, the driver would actually migrate the entire allocation potentially. Right? So you access one double, and it moves your entire 2 GB allocation back and forth. So that first access would be really, really slow, right? But afterwards, it's fine, because you move the entire thing. And in some ways, that approach actually has certain benefits, we'll talk about that later, over the second approach. That second approach is what you see commonly today. That's migrating pages over PCI Express. So most GPUs deployed today, in particular also in cloud systems, right, they hang off PCI Express buses, right? You have some x86 CPU, and then you have an H100, H200, Blackwell sitting on top of that. And the migration process, which is the default process there, the thing you get with like, CUDA managed malloc or malloc managed or HIP malloc managed and so on, is that it does page by page migration. So you have a big allocation, and what it then does is it migrates pages when it gets accessed either on the CPU or on the GPU, into its attached memory. And it does that on a page by page basis. The next one is unified memory on high-speed interconnect systems. The earliest one of that was the NVIDIA IBM system with NVLink in between. Now the most prominent example is Grace Hopper, right? So you have the ARM Grace CPU and you have a GPU, and you actually have a dedicated link between it. It isn't just PCI Express, but NVLink, right? And the typical deployments we have right now, we have almost a terabyte a second link between these two, right? 900 gigabytes. It's actually, I think in the first generation it was like 450 in each direction, right? So 900 bidirectional. But that's much, much wider than, say, your PCI Express connection is. And then the last version of unified memory, a true unified memory is actually, there's only single memory, is your APU. So in HPC, that's the MI300A, what we have in El Capitan. And in that, you have a single chip, a single die, with CPU cores and like GPU core clusters, and the whole thing just has HBM memory, right? It sits on the same NOC, it's the same chip. There is no like HBM and DDR memory, there's only one physical memory space, right? And all the cores can access that through the memory controller, right? Another example of that is laptop GPUs, right? Or laptop chips. That's very, very common, right? All your typical laptop chips have, this kind of APU design. That's true for Apple. That's true for, Intel and so on. Intel actually claimed for a long time, yes, they are a GPU shop. They ship the most GPUs in the world because, all their laptop chips had a GPU part and a CPU part. Your phone actually is kind of like similar, right? One other thing which plays a role in unified memory is the Linux Heterogeneous Memory Management. That was essentially the Linux kernel figuring out how to do this without like explicit hardware support, right? Initially in IBM, in the IBM Power thing, this kind of page migration stuff was in the hardware and only in the hardware. And in Linux, they've finally said, yeah, we need to deal with this situation, and we introduced that. What that basically does is there's potentially a software fallback for like page management, which does in the kernel during the kind of page faulting, etc., dealing with that process, and then migrating memory. And essentially, the Linux kernel now comes with interfaces which then vendors implement in their drivers for implementing the actual memory migration. So, I'm not actually going to show too much data today, because I have a very simple example which shows all the badness what's going on, and it's hopefully enough to convince you of a problem. So what I did here is this is a simple kind of like benchmark where I run a vector add on the GPU. Then I run that vector add twice on the host and then again on the GPU. Now, the code you see up there, that's like Coco's code, right? It doesn't really matter what you do with how you implement that, right? Cocos just sits on top of CUDA or HIP or SYCL or so on, right? So it's not like any magic thing. So the only thing it does there, right, with Perl 4 is either a GPU kernel dispatch or OpenMP pragma-based loop, depending on whether this execution space class there is like what we call a device execution space or a host execution space, right? So by passing in where I want to execute, right, this loop is going to execute on different places. So what I'm doing here is I allocated these vectors with essentially this kind of unified memory allocation, right? With CUDA managed malloc or malloc managed on the NVIDIA systems, and actually HIP malloc for the MI300A, because HIP malloc, it still gives you memory which is accessible on the host on the MI300A. And then I call that thing. I call it on the GPU, I call it on the host, I call it the second time on the host, I call it again on the GPU and again on the GPU. Okay? And the memory initially is on the GPU because that's where I initialize the views. Okay? And then I measure what is the bandwidth I get in each of these kernels. And I do that on an x86 with a V100 system, a Grace Hopper, and an MI300A. And so the initial data you see is roughly what I would expect out of the GPU, right? Like a V100 maximum stream throughput is somewhere around 820 gigabytes a second, right? This is a little bit less because it doesn't do any fancy 128-bit loads and stores and whatnot. Okay, but it's basically bandwidth, right? Maximum bandwidth. Same for the Grace, for the Hopper and the MI300A, right? I get like 3.4 terabytes on the Hopper and like 2.8 terabytes on the MI300A. It's a bit harder on the MI300A to get full memory bandwidth. Again, you need to jump through some hoops and not just do, I load a double and I store a double thing. The next thing is I run it on the host, right? And that's where the trouble starts. So on the PCI Express system, I'm now getting 10 gigabytes a second. That might not be too surprising, but I get only 38 gigabytes a second on Grace Hopper. And supposedly there's a 450 gigabyte one-directional link there, right? And I'm getting 38. On the MI300A, I get 178, which, may sound bad, but it turns out that if I run the kernel again, I'm only getting 197, right? Which is only slightly more. So the first call already gets pretty close to what the CPU can achieve when it runs on its own. There's only 24 cores per MI300A, right? So the 200 gigabyte-ish is kind of what you get if you don't jump again through all kinds of extra hoops to maximize bandwidth. The 60 gigabytes for this older x86 is roughly what you would expect, and the 320 gigabytes is roughly what you expect for Grace Hopper. Now, the next problem is I run again on the GPU, right? And now I'm getting 4.8 gigabytes a second on my PCI Express. I get 7 on my 450 gigabyte link, right? That's like, 60x loss in performance of what I expect. I do get the full bandwidth or close-ish to the full bandwidth on the GPU. And then the next GPU call gets me, again, back to the full place. Again, what I said is, right, 16 gigabytes is what the PCI Express 3 bus gives me. 450 is theoretical peak for this guy. So what's going on? One thing I can do is I run the same benchmark, but now I use explicit data management. Essentially, I put deep copies explicitly in, I make separate host allocations, and see what happens with that, right? And that's the green bars. And you see that the time goes down quite a bit. In particular, on the Grace Hopper system, right, I get 12x total time, right, for the 5 vector adds plus the deep copies. An interesting little quirk is, which I didn't see initially, is if I don't make a host warm-up call of my vector add for the MI300A, my MI300A performance is also really bad. So if I don't touch the memory on the CPU at some point, before I run the first vector add on the GPU, that first CPU vector add runs at 8 gigabytes a second. As bad or actually worse than the PCI Express one, even though no page moves physically, right? It's the same memory. So what is going on? What's going on is you're seeing the latency of page faults. All this performance penalty comes from page faulting. Page faulting is a rate-limited thing, and effectively the rate is somewhere, depending on your chip, between 5 and 8 gigabytes a second. It depends a bit on how large your pages are and whatnot, right? But that's what's going on. Who here knows what the page fault is? Decent number, good. For the other ones. So the way computers access memory is, right? You have an address and you dereference that. That address, what then happens is it looks it up, what kind of page does it belong to? Memory is organized in pages. These pages, depend on how you configure it, are between 4 kilobytes and even up to gigabytes. But the default is like 4 kilobytes on normal systems, and it's like 2 megabytes for MI300A for the HIP malloc. So it looks up what page might it be in, and it looks it up in a table. If it doesn't find that entry in that table, right, it will say like, oh, I have a page fault. I don't know what page this belongs to. How I map this virtual address to a physical address in my memory. And so it needs to go and update that TLB table. And that costs time. That costs quite a bit of time. And only when you have that, when you know how do I map this address, which is a virtual address, like when you allocate a gigabyte of memory, right? You start with some address and then you just increment the address to go through all the memory. But it turns out in physical memory that is not contiguous. Essentially, it finds places where it could put these chunks of pages, and then somewhere is this address mapping happening, right? From here's my virtual address to where is my actual physical thing, and that's this TLB thingy. And the problem is if the entry isn't there, it needs to update that, and that costs time, and that is what essentially only happens at that, single-digit gigabytes per second. Now, when can this still be working, unified memory for you? If you rarely access it on the host, right? Say you only initialize the data on the host, you load something in from a file system, then you access it on the GPU, and now you run 2 hours long simulation on the GPU before you dump something out again, right? Perfectly fine. Sure, the first move to the GPU is really slow, but you don't care. If you do rare I/O on the host, right, every 10 minutes you drop a checkpoint file, right? Probably fine. But you need to use a ratio here, right, of at least 100 to 1, right? We lost 60x on the Grace Hopper in performance going up and down, right, compared to even just the 450 gigabytes. It's actually more like a it's actually more like 500x or something like that, or 100x something compared to your memory bandwidth on the GPU. If you don't have that much reuse, if you use your memory 100 times on the GPU before you once access it on the host, you spend half of your time in that transfer, right? So your reuse needs to be way above that, right? If you're at 10,000 to 1, sure, no problem. If you're at 100 to 1, you're spending 50% of your time in that transfer. Right? Another thing is where it can work if you have very sparse access on the host. Right? So you have a gigabyte of memory, and the only thing you're going to need on the host is like these 5 entries somewhere. Right? Then, yes, the latency is high, but it's still faster to move that 4 kilobytes down than moving a whole gigabyte at the full bandwidth. Again, you need to hit a very large fraction of your pages, right? Even if you go through this and you say I touch every 1,000th entry, right? It's still bad because you're touching every single page, right? So your performance is still really, really, really crap. One thing which is often getting overlooked and which tripped us up quite a bit, we were like, yeah, everything runs on the GPU, everything is fine, right? But we are calling MPI. And you might be like, yeah, but that's not a problem, right? Because I have GPU-aware MPI. The GPU-aware MPI might end up disagreeing with you because it doesn't know where the unified memory allocations are, right? These allocations are accessible from the host. It can't figure out where the pages currently are. So it's just going to run the algorithm on the CPU, and it's touching all your pages on the CPU. So it's now pulling everything down at this low digits, bandwidth, sending it then over MPI, over the network, right? That transfer even limits effectively your network bandwidth, right? Which might be on supercomputers much higher than like 8 gigabytes a second. So you're even from that perspective, right, your MPI is now much, much slowed down, just the communication. But the worst thing about it is, yes, you pulled this down, but now the pages are on the CPU. Your next GPU kernel is pulling them all up again on a Grace Hopper at 7 gigabytes a second, right? And everything sucks. And the problem is, right, we just said the only way this doesn't hurt you is if you access your memory, if you go through all of your memory 100 or 1,000 times before you do another MPI call. And that's not how our solvers or anything like that works. So in Cocos, we're doing it slightly different, right? We do recommend explicit memory management. One thing we are doing is we have something called create mirror view. So I'll show you an example of that in a second, but basically what you do is you allocate your views, and then you create host copies via this function call. And what that function call does is it chooses the right mechanism to give you, a host accessible thing. If you only compile for CPUs, right, a Cocos code, this comes down to I just give you the same thing back, right? I don't create a new allocation. And that then means that the deep copy also becomes a no-op. The same is true for MI300A, right? If you compile your code, your Cocos code for MI300A, and you do that, there's only one allocation. Host A and A are the same thing. That means your deep copies and whatnot become no-ops. Yes, you expressed it explicitly, and it will do the right thing on Grace Hopper on your PCI Express-based systems, but it will also do the right thing on the CPU and the MI300A. You can opt into true unified memory with page migration by asking for the correct memory space, right? It's a type on your data structure. And so that means you have to opt in to the unified memory for the cases where it might actually still be beneficial, but it's not what we do by default. And this is then kind of like how this would look like, right? You create these mirror views of your vectors, you run your vector add, you call all the deep copies, and then you run another vector add, right? And these deep copies become no-ops on MI300A. Now, what I'm getting out of this, right, is unified memory can have severe and sometimes hard to predict performance penalties, right? With MPI stuff, for example, a lot of people wonder what's going on, right? Like they see their next kernel being really slow, and they're like, why is this kernel so slow? That doesn't make any sense, right? The first time I called this kernel, it was really fast. And the reason is page faulting. The exception for that is APUs. Now, the bad thing is we have the MI300A, but there's no other thing like that on the roadmap, on the public roadmap of any of the vendors, right, for HPC. Unified memory also works well if almost all accesses happen just on the device, right? If you have this 100x plus reuse, right, that can work. But if that's not the case for you, right, you really should prefer explicit memory management. We started out, when we ported Trillinos, we started out with a unified memory option. We essentially had a little flag which we deprecated a while ago, and we're actually ripping out right now in Cocos, which said, by default, we're going to give you unified memory allocations, so you don't have to put all the deep copies in. But then we spent years, reinserting all the deep copies and getting rid of the unified memory because performance was crap. Right? We never got the performance to a place where we were happy with it until we had, redone all of that stuff. Even in hindsight, it's not 100% clear to me if it would have been, faster or not to just start out doing it right in the first place. My slight gut feeling is that it would have been a bit better in aggregate total amount of work. That said, the benefit of getting some kind of results fairly fast, was useful at the beginning when people were still kind of skeptical of going to GPUs at all, right? But in hindsight, I would say today, where most people are convinced that we have to do that anyway, I think you're better off starting explicit immediately. So, conclusion, it's mostly a crutch. It's definitely not something I would do as a long-term strategy. And again, right, just to emphasize that, there is a real reason in the hardware, in the fundamental way our hardware works, that this doesn't get better, right? Page faulting is just a thing, right? And it is latency limited, and it's not clear that you can really fix that because it's kind of like a bottleneck, right? It's a kind of like, globally shared between all the threads, table you have to update, right? And doing conflicting or concurrent table updates in a shared table is just a costly thing, right? That's something we try to avoid in our own software design, but it is just how the hardware has to work, right? And so, don't do it. Okay, we have a couple minutes for questions before the next talk, if I'm not completely mistaken. Yeah.
So I have two questions. The first one, I guess, is kind of orthogonal to avoiding page faults, but it's already hard enough to avoid like cache evictions when writing performance CPU code. How does that relate to unified memory?
So you saw in the table earlier that there was slightly less performance in the first time I went back to the GPU, right? That was because of cache updates, right? Even on the MI300A, when you touch the memory on one side, right, it has to essentially invalidate the cache on the other side, right? And these additional cache updates cost you time, right? And that makes it so that even on MI300A, if you ping pong back and forth, you actually lose quite a bit of performance on both sides.
I see. So is it that you miss the virtual address lookup and then also missing the actual cache entry? So it's like a double. The
cache entry update is much faster than a page fault, right?
I see.
So you only lose like 10%, 20% of your performance or so, but that's what you get. you will see similar things for certain, as we have this thing called fine-grained allocation, where you actually can access the memory at the same time on both sides.
Oh, okay.
And if you do that, you actually lose like 20-25% global bandwidth, even if you never touch it on the other side, because every touch updates also both sides of the cache in terms of updating, what's happening.
I see.
Yep.
And then my second question is, I know for deep copies you do a no-op for unified memory. I was wondering, do you actually, in practice, do you implement it with a copy on write, or what do you do to maintain, like for the deep copy, like? So
the deep copy it's an implementation detail in Cocos, right? Where it turns out that on Grace Hopper, for example, CUDA mem copy is slower than actually just running a kernel to copy the stuff. So we're constantly looking at that, right? But the default is something like CUDA mem copy async.
Oh, okay.
Kind of style. Yeah.
Thank you.
Okay. The next speaker just said that he's not going to use the full 30-minute slot, so we can go through a couple more questions. Yeah.
So yeah, I'll just make this quick then. I mean, the problem with the TLB misses being so expensive is not a problem unique to this, right? I mean, if you're writing sequential code, it's a huge problem.
Can you go a bit closer? I don't hear you.
Yeah, I mean, so this problem with TLB misses isn't just a GPU, CPU problem, right? Being people, but in, so if I'm programming this in Linux, what I do is turn on huge pages, right? Then I have, 1% of the misses. Or huge tables, I guess whatever it's called.
Yeah, you can go to huge pages, right? Like the problem with that is that it makes your fragmentation issues much worse. And
yeah, with the scientific code.
Yes. So what we found is that huge tables makes significantly less available memory for our typical codes. So we actually, if you go to like gigabyte large pages or something like that, right? That actually has a significant impact on how big a simulation we can fit onto things. So we are not running that by default or trying that by default because it just doesn't work for most of our codes.
Okay, good, thanks.
So kind of related to, you mentioned the warm-up times on MI300s and the plots you showed. Is there any solution you've seen where like you could just go and touch all your pages kind of in advance before you actually run your kernel to kind of avoid that warm-up time, or are you just kind of screwed either way with that?
So in Cocos, right, we do that by default. We touch the pages on whatever the closest execution thing is. On MI300A, we do not touch it on both sides, right? We are not trying to go through it both on GPU and CPU. Maybe we should. Now, the thing there is that it's not as bad as, this initial, TLB update isn't really that bad, because the thing is that with the 2 megabyte pages you get with hipmalloc, your TLB actually covers your entire physical memory. And that means that update only happens once, right? Also that slow performance only happens once. After that, you're good, right? Because the pages never get evicted from TLB.
So I guess kind of related, we've noticed differences in timings, whether you use hipmalloc or hipmalloc manage. So you have kind of more time that you're kind of pushed towards the beginning of when you actually do your alloc, and then you're paying it, I guess, later maybe when you touch them. Yeah, I don't know. We don't really know what the balance is.
Hipmalloc manage has the problem that your aggregate performance is quite a bit lower because it uses these fine-grained allocations, and that means it does all this cache updating stuff, and so you lose, your bandwidth isn't 2.8 terabytes a second, it's 2.2. So we're not using that either. So unless you explicitly ask for it, for whatever reason you have to ask for it, and I would say, like, if you have a reason to ask for it, it's probably a violation of the Cocos semantics anyway, so don't do it. Yep. But yeah, so essentially it's not a problem there. It is a problem on Grace Hopper because your TLB is not large enough to catch everything, and your pages by default are not 2 megabytes, they are 4 kilobytes. So there, the slow performance happens every single time, basically.
Okay, cool, thank you.
And also the pages actually move, which means you do have to update all the time the TLBs, right? So even if if you don't overflow your TLB, right, it still has to update it every time because the pages actually physically move, right? On MI300A, they don't move, which means as soon as you have the initial entry in there, it's fine.
Cool. Thank you.